Welcome to Calculus and Vectors exam review for Unit 4, Trigonometry. We're going to start this one with just reminding ourselves what the actual derivatives are for all of the different trig functions. And we did some practice just working with trig functions, and if you remember, I think we're only really taking a look at now we'll see a bit of a trickier one as well. So we'll see a little bit more work, not too much though. But some of the derivatives, when you have something like cos squared x, like let's say 3x to the 4. There's a lot going on here, right? There's three different parts to this because you got to do the exponent part, the trig part, and then the angle part. So we're not going to see an example of that, so I would suggest making sure that you review some of that. We're going to look at a couple of other of the areas that we covered in this unit, but we did start out the unit practicing with some of that. So, but before we get to anything, we're going to remember what all of the derivatives are. So d by dx of sine of u. Now the reason why we do it this way is, notice I'm taking the derivative with respect to x, but my function is u. So that means we have to do chain rule here, which is the derivative for sine. See if you can remember these. If you can remember these from all those months ago, that's pretty good. Which one's which? These are the two most important ones. So this is cos u times u prime. That's the tricky part, is the u prime part. And d by dx of cos of u is negative sine u times u prime times the derivative of what's inside of the angle, right? Okay, and what are the other ones? D by dx of tan. Remember this one, secant squared. And d by dx of cotan. This one's negative cosecant squared. There's a lot of similarities between all these different ones that you can use, patterns sort of that you can use to remember them. And the last one is for secant. Remember what that is? It's secant times tan, again, times u prime. And notice these are secant tan. Those all go together. These ones on the left are all positive. So we can use that to figure out the very last one that we are going to do, which is cosecant. Now these don't come up anywhere near as often as the other ones. And this one is negative cosecant u cotan u times u prime. Okay, so those are the three primary functions and the three reciprocal trig functions and their derivatives. So our first question is just to find this is like the start of a curve sketch. Remember, sometimes we ask this funny question where we say determine and classify the critical values and the intervals of increase and decrease for the function below, in this case on a given interval because it's periodic. And people say, oh, I don't even know what this question is asking. It just means a first derivative chart. That's all this is saying. Do a first derivative chart like you were about to sketch, but you don't actually have to sketch. You don't have to do a second derivative chart either. Okay, so that's all we have to do. So we're going to start by taking the derivative. So I am going to take the derivative of sine, which is cosine, and then I'm going to be multiplying by the derivative of the angle. So I'm going to take that 2 out front. And then the angle stays the same, so you don't change the angle. So this was like derivative of sine is cosine of the same angle, and then times the derivative of the angle, derivative of 2x is 2. Minus 2 cos x, because the derivative of sine x is cos x, and the 2 was already there. Okay. Critical values occur when y prime is 0 or does not exist. Y prime exists for all x. Where does y prime equal 0? That's where 2 cos 2x minus 2 cos x equals 0. Well, first of all, we can get rid of those 2's. Now, what do you think we do next? Now, this is tricky because we can't have a double angle and a single angle. Like, we can't have our angles being different. So this has to be swapped out for a single angle using our double angle formulas. And we're going to keep everything in terms of cos. If I had a sine here, I'd be using the sine version, but this is cos, so I'm going to use the cos version. And the cos version is 2 cos squared x minus 1 minus cos x. So I'm going to rewrite this as 2 cos squared x minus cos x minus 1. And this is a lot like 2x squared minus x minus 1, which we will have to factor, and this is all equal to 0. Okay, so you just factor that like a trinomial, which works out to 2 cos x plus 1 and cos x minus 1 equals 0. So I got negative 2 cos x plus 1 cos x gives me negative 1 cos x, and everything else works out as well. Therefore, cos x is negative 1/2, or cos x is 1. So it looks like I'm going to have a bunch of spots here where we could have critical values. We're just going to 2 pi, so we do it on that regular interval. I'm going to use the graph for this. Cosine starts at 1 and ends at 1. So for this one, it's 0 and 2 pi. And for this one, I have to find the related angle, which is pi by 3. That's where cos is 1/2. You get that from the special triangles. Okay, and then we do x, and then it's negative, so we're in quadrants 2 and 3, so we get 2 pi by 3 and 4 pi by 3. Okay, so we've got 4 places where we have critical values, which may be local max, local min, or some kind of horizontal tangent line. So again, I'm going to do my first derivative chart. So I get x, y prime, and y. And we're starting at, and you would include the endpoints here. Now the endpoints of the interval are turned out to be critical values, but we would have included them anyway somehow. You can look back at an older example to see exactly how, because we don't just go x less than 1 or something, because it's not x less than 1. Periodic functions go back and forth and back and forth, so it's not like rational functions. At any rate, 0 less than x less than, what is our next one? 2 pi by 3, and then 2 pi by 3, and then 2 pi by 3 less than x less than 4 pi by 3, and 4 pi by 3, 4 pi by 3 less than x less than 2 pi, and 2 pi. So it was 0 here, 0 here, 0 here, and 0 here. Punching it into my calculator and checking, you're not going to be doing this one in your head, I don't think. You're going to be checking it on your calculator. So this one worked out to be negative, this was positive, this was negative. So this is decreasing, this is increasing. This is different from POIs where it's concave up, concave down. This is a first derivative chart, so it's just whether it's increasing or decreasing. Again, that was a fundamental idea that we explored early on, was if the first derivative is positive, then the original function is increasing at that point because the slope is positive, so you can picture that, right? Okay, so here we don't actually know what's happening. All we know is a horizontal tangent line, and if we were sketching, we could sketch that, where again we would just be coming up and we would be going flat, but that's where we would stop, because that's where we'd start in this case, but the beginning of the graph or end of the graph. That's all we know, and that's all we would need to know. We're not even doing that in this case. But we would just call that a horizontal tangent line because we don't know what happens after that. If it's going from decreasing, so it's coming down, and then it's increasing, Okay, decreasing, changing to increasing, well, that is a local minimum. Okay, and increasing, changing to decreasing is a local maximum. So we found the critical values. We didn't have to find the points in this case, just critical values. They were 0, 2 pi by 3, 4 pi by 3, and 2 pi, and we classified them. Whoops, except I forgot this one. And we classified them as local max, local min, or in some cases, all we know is it's a horizontal tangent line. Okay, so that's a first derivative chart. You could get that with rational functions, polynomial functions, trig functions, logarithmic functions. I mean, you could have the general idea of a first derivative chart with any kind of a function, but that's how you do it. Take the derivative, where does it not exist, where does it equal 0, and then there's also some review on trigonometry and how it works, solving a trig equation, solving those little equations that come out of it to get the actual critical values, and then the first derivative chart. Okay, and finally, this is the only other question for trigonometry we're going to do. Find dy by dx for this function. Now, what do you notice about this function? Well, I noticed that it is implicit. So we have to do implicit differentiation for this. And it's got a tan in it, so it's got a little bit of trig, but then it's also got just some non-trig stuff, the 3xy. And there's something about that 3xy that we have to remember. Do we remember what that is? It's product rule. It's sneaky because it just looks like one term altogether, but it's x times y, so it is product rule. So let's get started on this. We can go right back up tan of 4y and see that the derivative of tan is secant squared. So I'm going to get secant squared, angle stays the same, and then times the derivative of the angle, so times 4. So I could have taken that 4 right out front if I had wanted to. If I didn't notice it, then I can do it at the end. And whenever we're doing the derivative of y, what do we also have to include? dy by dx. Now this is product rule. So the derivative of the first thing is 3 times the second thing, which is y, plus derivative of the second thing, be careful, it's dy by dx, times the first thing, which is 3x. I left the negative all the way out front, so I'm not worrying about the negative. So I've got 4 secant squared 4y. We have to now solve this for dy by dx. That's what we're supposed to find, not just a one-line derivative. Rarely do we do that. Minus 3y minus 3x dy by dx. Whoops, and I'm missing something. Equals 1. Derivative of 1 is 0. So all of this is equal to 0. That way I can move everything to the other side. So I'm going to take 3y over and factor this other side. So I get dy by dx. And I get this left over. Minus 3x. So I factored the dy by dx's out of those parts, equals 3y. One more step. And there we have it. We've written it out in terms of, we've simplified for dy by dx. We're not going to be able to do any more work with this like we did with logarithmic differentiation and those kinds of things. So in this case, I believe we are done. And that's it for trigonometry. It was short and sweet. We did a little bit of sketching. And again, some of the other questions, like some of the more complex derivatives or finding equations of tangent lines for trig functions. We can find equations of tangent lines for anything, so that's something that might come up, but those were some of the general ideas that we did in trig. In particular, that first derivative chart reminds us of some of the intricacies and uniqueness of what it's like to do it for trigonometry. But that is it for Unit 4.